So the first thing we need to do is just load the extension. So I go to Extensions, Manage Extensions, choose ASME Design by Analysis, close that, and then I can add a simulation. Choose the ASME Design by Analysis extension. Okay, so the first thing it asks of me is to browse to my geometry file. If I don't know what to do, I can also just click on all of these question marks and it will give me an explanation, or I can read here on the right the description. So let's browse to the geometry file, solid model insert. Okay, and then I have to define my simulation goals. So by default, I'm going to do a protection against local failure analysis. I can choose to add protection against plastic collapse and ratcheting assessment. So these simulations come from ASME VIII Part 2 Division 5. ASME VIII Division 2 Part 5. Okay, so the first one, protection against local failure using the elastic plastic analysis method. So it will be this one, 5.3.3. Essentially what I'm going to calculate is this local limiting triaxial strain, and then also the strain utilization factor. So what this equation 5.7 says is equivalent plastic strain plus forming strain should be less than the limiting triaxial strain. So the utilization factor is essentially just this one, the plastic strain plus the forming strain, epsilon CF, divided by epsilon limiting strain. That should be less than 1 for a pass. Okay. The second analysis is protection against plastic collapse. Also, again, using the elastic plastic stress analysis method, this 5.2.4. Essentially what it says is that you need to reach convergence for your specific load case. So the most severe one would be a load factor of 2.4. If you reach a load factor of 2.4, it's a pass. Also, if you use the elastic plastic stress analysis method for checking for plastic collapse, it also doubles as a check for collapse from buckling. So if I go to protection against collapse from buckling, go to 5.2.4 numerical analysis. Where is it? Okay, here it says 5.4.1.2. If a collapse analysis is performed in accordance with 5.2.4 and imperfections are explicitly considered in the analysis model geometry, the design factor is accounted for in the factored load combination. So essentially, if I am doing this protection against plastic collapse using the elastic plastic stress analysis method, and I am including all the geometry, it doubles as a check for protection against collapse from buckling. Okay, the last one that you can choose currently is protection against failure from cyclic loading, and here we can choose ratcheting assessment, elastic plastic stress analysis. Okay, so essentially we're doing 3 consecutive loads. So assign the load, take the load off, put the load on again, take it off, put the load on again, take it off. Okay, the next thing, amount of ASME materials in the model. So here I have the option to choose 5 materials. So what it means is, for each one of these materials, the local limiting triaxial strain will be calculated, as well as the strain utilization factor. Then I can choose part interactions. So by default, contact will automatically be set up in my model. The target accuracy, so this is the mesh control. I can choose quick, medium, or high. So I will just choose high. Submit to analysis. This is just what's going to happen when I'm finished with my definition. So you can click on next. And now here at the bottom you can see it's sort of starting to create the setup, import the geometry. here I have my geometry. So once again, as with the other steps, I can read what is required for me here at the right hand side. I'm just going to hide it. First thing I have to do is assign my material property 1. So in my first step I said I only want to check one material. Now I have to define where that one material is. So I can choose, make my body selection, my filtered body selection, choose the cylinder, add, choose this little solid section here, add, and I can choose my material type. So this comes from table 5.7. So if I just load this up again, table 5.7. So to find that, I can just go to protection against local failure, table 5.7. In here. This is basically what I can choose from: ferritic steel, stainless, duplex, superalloys, aluminium, copper, titanium, zirconium. And what it's going to do is it's going to calculate these factors for me, or these variables. So M2, this alpha, and also elongation. So let me choose stainless steel in this case. I can define the Young's modulus at operating temperature, Poisson's ratio, the density, tensile yield strength, tensile ultimate strength, elongation, or area reduction. So it will use the biggest one of these two, and also I can specify a forming strain. Now where do I get these variables or properties? I can just go to Section 2, Materials, as in Boiler and Pressure Vessel Code, Part D. This is where I will get all my properties. Okay, and then I have the option to say, generate ASME plastic stress strain curve. I have the option to say, I want to do an elastic perfect plastic material, or generate a full stress strain curve. So in this case, let me choose full stress strain curve. So based on the material type and tensile yield and tensile ultimate, elongation, Young's modulus, all these things, it will generate automatically a stress strain curve for me. So if I click on next, I will get this little pop-up saying stress strain curve written to file, and this is where that file is. So let me open that file quickly and show you what it looks like. Okay, so for each of those materials that I define, and I can define a maximum of 5, it will give me my plastic strain versus stress curve. So let me just insert a graph here. That is what my stress strain curve for that specific material looks like. So here on this axis I will have my stress, and here we'll have plastic strain starting at 0. Okay, don't want to save it. Okay, next thing I have to do is assign my pressure application region. So you can change my filter to face selection. I want to choose all these faces. Hide this body. And select the internal faces. Now I can set my design pressure P. I have to tell the program where is the vertical direction, or what direction is vertical. So in this case, positive Y. So I just say Y positive. I also have the ability to include hydrostatic pressure. So how I do that is essentially I have to give the fluid density. In this case, let's make it water. And I have to specify the free surface height. So that is where pressure is 0. So in this case, let's make it about 1,000 millimeters. So it uses this Y direction, the global Y, to calculate the hydrostatic pressure in the downward direction, and it will be 0 above the free surface height. Okay, and the last thing I have to do is select my support locations. So I can just select all these ones at the bottom. And just save this. And that's all I have to do. Now I can just click next. Now it is automatically setting up all the analysis, 3 of them. And it will also automatically submit them to the solver. Now I can track these simulations by going to solution monitors, and here I have 3 charts. So first one is chart 1, local failure, chart 2, plastic collapse, chart 3, ratcheting, or I can go to transcript and the same thing. I can look at the output while it is solving for transcript 1, local failure, transcript 2, plastic collapse, and ratcheting further. So let's click on local failure. I can see it's already started solving. Let me click on solution monitor and to update now. Okay, so there it starts updating. So this I can quite easily track if my simulations are running. Once it's finished, this is my view. So here I can see local failure. It reached the target of 1, that's finished. Chart 2, plastic collapse. It reached the target of 1, that means it converged. The next one, ratcheting. Again, target of 1, it's finished. So let me just close this. So what I get is this little report where it tells me maximum strain limit utilization factor 0.001, and I can also plot it. So currently it is set to plot the utilization factor, and I can zoom in here and I can see this is where the maximum is. I can also see when I switch on my mesh that the mesh is very, very rough or coarse, and probably this is not converged yet. But it's a quick way for me to see if I might have a problem or not. So because it is less than 1, it tells me the maximum strain limit utilization is a pass. Next thing it tells me, maximum plastic collapse factor is 2.4. So it's a pass because the requirement is that I reach the maximum load factor, which is 2.4. I can plot the plastic strain result. And here it tells me this is also the area where I have maximum plastic strain, 0.02. So it's also quite a small amount, 0.2%. Last thing, I can plot ratcheting. So what it tells me is residual plastic strain increase over 3 ratcheting cycles is 0. So what it essentially means is After I've removed my load 3 times in a row, so what I did was I applied my load, I removed the load, then I applied it again, then I removed it, then I applied it again, then I removed it. So there is 0 residual plastic strain. So one of the requirements for this ratcheting assessment is that I should have 0 plastic strain. And in that case, I don't have to look any further, it's a pass. Okay, but so like I said, this mesh is probably way too coarse to make a call. So let's go and refine this mesh a little bit. So I can click on finish. So let's go back to my mesh. So let's add some local controls. So I can say body sizing. Let me change the filter to body. One volume. Let's make it 8 millimeters. Let's add another control, face sizing. I want to make this wild face 2 millimeters. And the last one I want to do is the edge sizing. So we change the filter to edges and choose that edge. Control select that edge. Control select that edge. Control select that edge and add it. I'm going to say make it 8 mil as well. And generate mesh. Okay, so as you can see, this is much more refined. Let's go to protection against local failure analysis. So let me just show you some other things that you get. So the first thing for this protection against local failure analysis, you can see the loads I'm using, design pressure times 1.7 factor, hydrostatic pressure times a 1.7 factor, gravity times a 1.7 factor. Now, if you need to add things like nozzle loads, this is also where you can add them. So I can just go structural conditions, add a force or whatever extra load you're interested in. Because I'm using a plastic stress strain curve, it is not supported by default in the AIM interface, but what happens for each material is a little snippet is generated with the plastic stress strain curve in there. Okay, so let's run this simulation. Okay, once the result has been updated, I can see on my chart local failure is finished. Let me close that. Open my results. Here I have a few contours. So what I'm after is this strain limit utilization factor. So let me just select this one. I can turn off my mesh. So I can see, we turn my mesh back on. So currently I'm sitting at 0.01 utilization factor, so it's still quite far below the limit of 1. So in this case, I don't really have to do anything more. This is a pass, and the rest of my model, there is really nothing going on. So yeah, I'm finished for local failures. I don't have to do any stress classification lines or things like that. Now I can go and update my plastic collapse analysis with the new mesh by just right clicking and selecting evaluate results, and then I can do the same for the ratcheting assessment evaluate results.